We discuss some of the antenna parameters like input impedance, then fields, far field region, near field region, radiation near field region, reactive near field region, then antenna pattern, TD pattern. We define what is antenna pattern. So now we will discuss about the radiation pattern, continue with the radiation pattern. In the last class, we considered the two-dimensional radiation pattern. 2D radiation means if you are looking at the pattern in a particular plane, and if you are looking the radiation in a particular plane. So if you take a plane, so in the 3D, take a cut plane, and in that plane you look at the radiation, how the radiation is distributed over that plane, that gives you the 3D radiation pattern. But instead of taking a plane, if we consider all the three dimensions over the whole three dimension, how the radiation will be distributed, that will give us the 3D radiation pattern. So we'll consider the 3D radiation pattern now. The 3D radiation pattern, purpose of looking at the 3D radiation pattern is looking at the complete radiation in the space over the space, how the radiation will be distributed over the space. So it gives you the complete view of the radiation pattern on the three-dimensional view means 360-degree view, and it will be easier for quantifying the radiation characteristics. So radiation pattern characteristics can be easily quantified if we know about the 3D radiation pattern. Now, this is an example of a 3D radiation pattern. If you can see, here is a 3D pattern. There is a beam, a large beam, then there are smaller beams, and they are coming out from a source, which is the center where the antenna is. So from that point, it comes out. Now, what is a 3D pattern? It gives you good overall impression of the entire radiation pattern that is given by the 3D, and that is what is 3D pattern. It gives us a overall good overall view. That is what is a 3D pattern. Hi, but from the 3D pattern, in the 3D pattern, you cannot you cannot get quantitative information clearly. For getting quantitative information, we have to take a cut plane in the 3D pattern, so that and the pattern will be available on a plane. On that plane, in any one of the principal planes, that E plane and H plane, there you will get the information. What is the beam width? What is the side lobe? Those things we can get there. So therefore, the 3D pattern comes from the 3D pattern as chords in the 3D pattern. For example, let us see two chords we know. One is the two principal patterns, the E plane pattern and the H plane pattern are the two chords in a 3D pattern. So one containing the E field, other containing the H field. One is in the vertical direction, or one plane passing through the H, that gives you the E plane pattern. So one plane passing through the Z axis, so that gives you the E plane pattern. Other plane passing through the XY plane, that gives us the H plane pattern. So these are the two principal patterns. They are called E plane pattern and H plane pattern. That we have seen in the last class we discussed. These are the two popular patterns, popular plots. Now in these plots, what we do is we take a cut for a fixed phi value, because phi is in the xy plane. So take a fixed phi value, then take a plot of which passes through the z axis in the plane for a fixed phi value passing through the z axis. That in that plane, the variation will be, since phi is fixed, variation will be only theta. So along theta there will be only variation. Similarly, take a fixed theta value and then take the cut in the phi plane through the antenna, passing through the antenna. That gives you the Their phi will vary, theta will remain constant. Then on the side lobes, you can see there is a main lobe. Main lobe means the amplitude is maximum. That we call the main lobe. And other amplitudes which are appearing on the sides of the main lobe, those are called the side lobes. So the side lobes are alternatively positive and negative valued here when you take a cut on a fixed phi value plane. So those will be alternatively positive and negative value. Usually what we do is when we consider the this is for the radiation pattern or the E field pattern. But if you consider the power pattern, power pattern E becomes E square, therefore there will be no negative value, everything will be positive. So all those positive peaks, negative peaks, they will flip and they will come on to the XZ plane. Okay. Now let us define what is side lobe, or let us see what is side lobe. We will consider for this, I will consider the the field pattern, not the power pattern. Let us consider the field pattern. Now you can see there is a main lobe in this figure. There is a main lobe, and its amplitude, peak amplitude is 1. What is that? How do you get the peak amplitude of 1? You take an antenna, draw the pattern, no, sorry, take an antenna, find out the field values for different angles. So suppose it is along Z, so find out the field values for different theta. So as theta varies, there will be different field values. From that, find out which is the maximum value. With the maximum value, divide everything, all the values divide with maximum value. So when maximum value will be divided by maximum value, that will give you 1, and that will be the maximum. And other values, since they are less than maximum value, they will give you less than 1. So this one division is called normalization. We are looking at a normalized pattern. So this gives you a normalized pattern. So we'll find out what is the side lobe level or relative side lobe level. The side lobe level, now if you look at there are two beams. One beam is the major beam. Other beams are called the minor beams. So on the major beam, this is a uh, pattern which is in spherical coordinate system. So it varies with theta and phi only. Now, what does the side lobe level give us? They give us the measure of power concentration in the main lobe, the main beam. Sorry, the main beam gives us the measure of power concentration in the main lobe. Now, if the and the ratio of the pattern values of a side lobe peak to the peak value of the main lobe gives us the side lobe level. So if you look here in the figure, there is a larger beam which we call the main lobe. There are smaller beams at the base of the larger beam which we call the minor lobes. So main lobe and minor lobe are there. The two minor lobes which are adjacent to the larger beam, they are called the side lobe because they are on the two sides and two sides of the main lobe, and they are connected to the main lobe. So we call them the side lobes. All other lobes are called minor lobes. The minor lobes can be, there can be minor lobes, there can be back lobes. We'll discuss about that later, but let us concentrate on the side lobe. So there will be some power, there will be maximum power in the main lobe, then there will be some power in the side lobe. So if you look at the side lobe, there will be some power in that side lobe. So if there is some power in the side lobe, the side lobe level will be the ratio of the power available or ratio of the field available in the side lobe to the power available in the main lobe. So that will give us what is the side lobe level. So the ratio of pattern value of the side lobe peak to the pattern value of the main lobe peak, that gives us the side lobe level. that is called SLL. SLL stands for side lobe level. The SLL, this gives you the largest side lobe level for the whole pattern, and on the maximum, relatively maximum side lobe level is given by this SLL. Now, if you express it in dB, then SLL dB is equal to 20 log FSLL by F max. What is FSLL? F is for the field pattern. F stands for field pattern. So field pattern of the SLL, peak value of field pattern of the SLL by peak value of the field pattern of the main beam. That is F max. So that is SLL in dB, 20 into that much of dB. So for a normalized pattern, F max that you know 1. So SLL dB is equal to 20 log F SLL. So that will be for a normalized pattern. So we are drawing a normalized pattern. Therefore, SLL dB will be equal to 20 log F SLL. Now, in this, let us define the next characteristics, which is called the half power beam width. Half power beam width, we define it by considering the power. Now we have a field pattern and power is equal to E square. We know E is the field and E square, power is proportional to E square. So P is proportional to E square. When power will be half, the E square will become E square by 2. Now look at the main lobe. Maximum power is for 1. When E is equal to 1, we get maximum power. Then when E has square, so or if E is equal to 1, E square is equal to 1. So there we get maximum power. Then E square is equal to 1 by 2. E square is equal to 1 by 2 means E is equal to 1 by root 2. So E is equal to 1 by root 2. 1 by root 2, if you calculate it, it will be 0.707. So on two sides of the peak value, which is 1, there will be points which are 0.707. So, or if the main value, if we are not drawing a normalized pattern, then what we'll do is whatever is the maximum pattern, multiply that with 0.707 to find out the half power value, where we will get the half power value. So on the left hand side, we will get an angle for which power is half, or if E value is, or field value is 0.707 of its value at the peak. On the right hand side also we will get a point, an angle for which power is half, that is called half power point. These 2 points are called half power point, and the angular separation between these 2 points is called half power beam width. So angular separation between the two half power points is called the half power beam width, or HPBW. HPBW stands for half power beam width. This half power beam width quantifies the main beam. Usually this is one way of quantifying the main beam. There is another way that we'll discuss, but this is what quantifies the main beam mostly. This is the angular separation of points in the power pattern main beam, where the power peaks equal one half of the maximum value. And analytically you can write HPBW, half power beam width, is equal to theta half power on the left side minus theta half power on the right hand side. Amplitude, the absolute value of these and two differences. That gives you the half power beam width. Then there is another beam width which we call the fast null beam width, or a beam width of fast null. BWFN is the fast null beam width. Now look at the main beam and look at the side lobe. So main lobe and side lobe, in between these two lobes, there is a space where you can see that there is a space for which the field value is 0. So the point for which the angle for which the field value is 0, which is adjacent to the main lobe, the angle for which field value is 0 on the left hand side, the angle for which field value is 0 on the right hand side of the main beam, and consider the angular separation between these two angles. That angular separation is called the beam width between the first nulls. When it is 0, 0 means null, null means 0. So the since a null occurs or a zero occurs, no field is there. So this is called null, and the separation between these two is called the beam width between fast nulls. This is the fast null. Then from the side lobe there will be another null side lobe, and the minor lobe there will be another lobe. Now all these minor lobes except the first two lobes which are adjacent to the main lobe are called minor lobes. Only the first two lobes which are adjacent to the main lobe are called side lobes. Now these minor lobes can be also categorized. Now what we'll do is draw a horizontal line passing through the origin. So passing through the source where the antenna is there, that is the origin or source. So draw a horizontal line passing through the origin. All lobes below that uh, uh, line are called the back lobes. All other lobes except the main lobe, all other lobes are minor lobes. Among the minor lobes, the lobes which are adjacent to the main lobe are called side lobes, and all other lobes, then all other. So main lobe, side lobe, except those others are pure minor lobes. Among the minor lobes, which are below this line, which passes through the antenna or passes through the source, on the horizontal line, which occur below that line, those lobes are called the back lobes. So we have three types of lobes. One is the main lobe, then the side lobe, then minor lobes, then back lobes. Back lobes are a type of minor lobes. Side lobes are also a type of minor lobes. Now we'll be categorizing antennas. This is called antenna referencing, or let us categorize antenna according to the pattern of the antenna. So if the antenna is producing a particular type of pattern, then we'll categorize or classify the antenna. So this is called antenna referencing. Let me give you some example. First example which comes to mind is the isotropic antenna. In the isotropic antenna, it is a fictitious antenna or a hypothetical antenna. It does not exist in real world. So it is an hypothetical antenna. This radiates equally in all directions. That is its property, main properties. It radiates equally well in all directions, and so since it radiates equally well in all directions, it has a constant radiation pattern in the space. Over the space, it has a constant radiation pattern. Then the next antenna is very common, which is called the omnidirectional antenna. For example, it is a ideal dipole. This is a omnidirectional antenna. Now, omni means omnipresent, means present everywhere. So omnidirectional, it has a direction everywhere in all directions. So this has a pattern which is constant in one plane, not in all planes. It has a constant pattern in one plane. This is not hypothetical, this is realizable. For example, it is a ideal dipole. This has many practical applications. We'll discuss the practical applications later, but it has many practical applications. For example, cell phone antennas, they should respond equally from all direction in the horizontal plane. So they have to be omnidirectional. Base station antennas, they need uniform coverage to serve users on the ground. So they are another example of omnidirectional antenna. So these are two examples of antennas. I'll consider some other examples also. Now look at this pattern. This pattern, the main beam, looks like the blade of a fan. old days fan. Nowadays the fan blade does not look exactly like this, but earlier the fan blade was looking like this, almost similar to this. Therefore, this beam is called uh, a fan beam. And this is if the antenna is uh, along the on the xy plane, along the x-axis or y-axis. This beam is around the z-axis, and this is called a broadside antenna. So if you have an antenna which radiates in this manner, then that is called a broadside antenna. Antenna is along the x-axis or y-axis or on a line in the xy plane, and it is radiating in the z plane. Its main beam is in the is around the z-axis. Then that antenna is called the broadside antenna. So the main beam maximum is in a direction which is normal to the plane containing the antenna, and that is what is called a broadside antenna. An example is a again an ideal dipole, properly oriented ideal dipole will give you this type of beam. So if the beam on the other case, look at the other antenna, and the beam is on the plane of the antenna. So that is called the end fire antenna. The main beam maximum is in the plane containing the antenna. If the plane containing the antenna contains the main beam maximum, then that is called the end fire antenna. So we have two types of antenna. One is broadside antenna, other is end fire antenna. Between these two types, these are the two extremes. One is perpendicular to the antenna, beam maxima is perpendicular to antenna. Other is beam maxima is parallel to the antenna, along the antenna. Suppose you have a linear current on the z-axis. The broadside direction will be theta is equal to 90 degree, and the end fire directions will be theta is equal to 0 and 180. So if you have a linear current along the z-axis, on the z-axis, so since the antenna is on the z-axis, so broadside will be perpendicular to z-axis, therefore theta will be 90 degree. And fire will be along the z-axis, so therefore theta will be 0 degree or 180 degree. Now between these two antennas, all other categories of antennas are between these two. So all other are intermediate are type of antennas. Either they are end fire or broad fire side. These are two extremes, or between these two extremes. All other antennas will be between these two extremes. They may not be end fire or broadside, but they will be between these two extremes. That is what is the third figure, central figure shows you, which is neither broadside nor end fire. We have formed a beam in a particular direction. Maybe it is 60 degree direction. There it is it has the maxima, beam maxima is along that. Now these are antenna referencing. Then let us come to the radiated power, power radiated from the antenna. So then you know the what is pointing vector power. The moment we say power, it is electromagnetic power or electromagnetic energy. Electromagnetic power or energy is related to the Poynting vector, because Poynting vector gives a power density, and it is defined as S is equal to 1 by 2 E cross H star. So Poynting vector is equal to half E cross H star watts per meter. Now power flowing out through a closed surface, we can find out from the Poynting vector by integrating the Poynting vector over the surface. So P is equal to integration of S dot ds, and ds being the surface, S being the surface, capital S being the Poynting vector. So power flowing out through a closed surface is given by this. So this is the power radiated by the antenna. If energy coming out of this is this, then power radiated by an antenna will be P, that will be equal to 1 by 2 eta integration over E theta mod square plus E phi mod square into R square d omega, because R square d omega will give you the surface integration over the surface. Then E cross H, as you know, E cross H will be E cross E star by eta. Now E cross E star by eta, then we consider the two components, that is E theta square plus E phi square. This we have discussed in the electromagnetic class. Therefore, I am not going into this. 1 by 2 comes from the half term, and eta term comes because H is equal to E by theta, E by eta. So from that you get E eta. Then mod term comes because E cross H star we are considering. So that is E cross E star. When you can take E and multiply it with E star, that gives you mod of E. So there are two components, E theta component and E phi component. So from that you get E theta square plus E phi square. So that gives you the power radiated by an antenna. So if you know the field, what is the field of the antenna, E theta field, E phi field, you can find out the power radiated by the antenna. Once you know the power radiated by the antenna, then we will define a quantity which is called the radiation intensity of the antenna. What is radiation intensity of the antenna? This is the power radiated in a given direction per unit solid angle. This is the definition. Power radiated in a given direction. So direction is fixed, which means theta and phi are fixed. So power radiated in a given direction or power radiated for a given theta and phi per unit solid angle. Units will be, since it is power per unit solid angle, so units will be watts per square radian. So watts per square radian or steradian. This is called steradian. Because solid angle is given as steradian. So watts per square radian or watts per steradian. Advantage is power radiated is independent of distance r. It is not dependent on r because we are considering area per power radiated per area at any distance r. So everywhere it will be the same. Power radiated per area will be same. So that is the advantage. It is independent upon distance, independent of distance. Radiation intensity is independent of distance, and it is power radiated per given angle, power radiated in a given angle per steradian or per unit solid angle. Now, how do you express this? What is the expression for power density? Power intensity. Power intensity is given as U theta phi. So U, once you fix theta phi, that will give you the intensity. So U theta phi is equal to 1 by 2 real part of E cross H star into R square R cap. So it is along the radial direction. So it is independent upon radial direction, but it is along the radial direction. So why it is along the radial direction? Because you will find out the power intensity at a particular distance along the radius. So as you move along the radius, you will find out the radiation intensity. That is why it is R cap is there. So U is equal to this. That you can write as S theta phi into R square. Now S theta phi has a R square term in the denominator. So numerator and denominator R square will cancel out. Now U theta phi, that is UM is the maximum power, UM F theta phi square. So is the maximum value of U theta phi. So if you have U theta phi for different theta and phi, find out what are the values of U theta phi. From that you find out what is the maximum value. So that gives you the UM. So UM into F theta phi being the normalized field pattern. So F theta phi square. U theta phi is equal to UM F theta phi square. F theta phi being the normalized power pattern. F theta phi square is the normalized power pattern. Okay. So from that you will get UM is equal to U theta max and phi max. So U for the radiation pattern for theta max and phi max. It does not mean that theta is maximum, phi is maximum. It means that the theta and phi values, theta value for which U is maximum, phi value for which theta U is maximum. That is what is indicated by theta max and phi max. And then comes the average radiation intensity. This is the radiation intensity. Then the average radiation intensity, that is equal to the radiation intensity u theta phi that an isotropic source with the same input power P would radiate. That is what is called average radiation intensity. So U average is equal to 1 by 4 pi integration of u theta phi d omega, or that is equal to P by 4 pi, because an isotropic source radiates equally in all directions. So therefore you get 1 by 4 pi, all directions you take 4 pi steradian. So it will be 1 by 4 pi comes from that. So U average is equal to 1 by 4 pi integration u theta phi d omega. D omega is the solid angle, integration over solid angle. So u theta phi, you are integrating it over the solid angle and dividing it by the total angle, which is 1 by 4 pi. So that is what is u average. So average intensity. Now we will come to the directivity of the antenna. Now directivity of the antenna, look at the antenna here. We have the antenna, we have the main beam in a particular direction. So you have the main beam. Then by directivity, what we do is, suppose antenna is radiating p watts, maximum radiation is p watts in a particular direction. Then you replace the antenna with another antenna which is isotropic antenna. So if you have isotropic antenna, the isotropic antenna is also radiating p watts. And now but isotropic antenna is radiating p watts in all direction. This antenna is radiating, your antenna is, practical antenna is radiating p watts in a particular direction. Then we find out the ratio of radiation intensity in a reference direction to the average radiation intensity which comes from the isotropic antenna. So take the average intensity, so then that will give you the directivity. So directivity is the ratio of the radiation intensity in a reference direction. Usually the reference direction is the direction in which you have the maximum radiation. So in the reference direction to the average radiation intensity. Average radiation intensity you find out by considering an isotropic antenna radiating the same power. Then find out what is the power intensity of the isotropic antenna. Then divide these two intensities. So by default, the reference direction is the maximum direction. Directivity D is equal to um by u average. So that you can write, and u average we have seen that it is p by 4 pi. So it will be um by p by 4 pi, or that will be 4 pi into um by p. And since um and u average both have same unit of power, therefore their ratio will be unitless. So directivity does not have uh, does not have any unity. So directivity is a number, simple number without unity. Now you can write directivity D is equal to um by t, um by r divided by u average by r. So numerator and denominator we divide by r. If you divide the numerator and denominator by r, in the numerator you have got um by r divided by, in the denominator you have got now p by 4 pi r. So that is another definition, another way of undefining directivity. So divide numerator and denominator by r. So this is equivalent to power density at a distance r from the antenna, because P by 4 pi r gives you the power density at a distance r from the antenna. P is the total power. So at a distance 4 pi r, you get the power density. At a distance r, 4 pi r is the surface enclosing the antenna. So therefore P by 4 pi r is the density. So this is equivalent to power density at a distance r from the antenna. Now what are the physical interpretations of this? Uh, So on the physical interpretation, it is, this gives you the ratio of maximum to average radiation intensities, which is dimensionless, a ratio of maximum to average power densities, which have units of watts per meter square. So we have got two things, a ratio of maximum to average radiation intensities, that is power unitless. But if you consider ratio of maximum to average power densities, that has units of watts per meter square, which is the average power density has the unit of watts per meter square. Okay. Now look at this. We have uh, the interpretation of directivity. Actual pattern is shown on the left hand side figure. That is the maximum pattern, maximum intensity is Then I am showing a solid angle, unit solid angle passing through that So where you have got from that point, take the unit area there, and subtend an angle onto the antenna. So antenna is at the center. So subtend the angle, that gives you omega A. So omega A is the antenna, the solid angle at the antenna. So you have got the same contained within this solid angle. If you have got this solid angle UA, which contains the same power then what will happen, that we'll consider. So this is equivalent to this. This actual pattern contains the maximum power or average power and that is contained within a solid angle UA. So from now we'll consider the directivity. So if these two are equivalent, and once these are equivalent, then we'll define what is called the beam solid angle. The beam solid angle omega A is the angle subtended at the antenna by a solid angle. So omega A will be equal to integration over f theta phi square, which is the power pattern, or the d omega. So integration of the power pattern over d omega, that gives you omega A, which is called the beam solid angle. Interpretation physically, what do you understand from this? It is the same solid angle as constant radiation of a level equal to the maximum value radiation intensity over all the beam area. That is what is beam solid angle. Beam solid angle is the same solid angle as constant radiation of a level equal to the maximum value radiation intensity over all the beam area. So that is how you interpret it. So by that interpretation, we can write P, total power P, is equal to high integration f theta phi square d omega, that is omega A. So on that power definition we know integration f theta phi square d omega. So that you can write now remains as it is. Integration f theta phi square d omega is omega A. Therefore P is equal to into omega A. Now U average is equal to average intensity, that is equal to P by 4 pi, that we know. D directivity we know by U average. So intensity maximum intensity by average intensity, that we know. So now maximum intensity by average intensity. For average intensity you write P by 4 pi. So D is equal to by P by 4 pi. Now that you can write as by for P you write into omega A. So divided by omega A into divided by 4 pi. Now in the numerator denominator cancels out. 4 pi goes to the numerator. So U average intensity is equal to 4 pi by omega A. So if you omega A means beam solid angle. So average intensity is equal to 4 pi by beam solid angle. So pattern shape determines the directivity. This implies that the pattern shape ultimately determines the directivity. Directivity as a function of pattern angle will be given by d theta. D is the directivity, that is equal to d into f theta phi square. So directivity. And now what is the d on the right hand side? that is the maximum directivity. So, and d theta phi as a function of pattern angles will be d, which is 4 pi by omega a. So that d, that is that the d on the right hand side, that into f theta phi square, that gives you the directivity as a function of pattern angle. And now, what is the concept of directivity? From where we get the concept of directivity? Consider this: U average is over the sphere. So at the center of the sphere is the antenna, and the sphere has a radius r. So at a distance r from the antenna, everywhere on the on this we have a sphere. On the sphere, on the surface of the sphere, everywhere you find out the radiation intensity. Now, if you have an isotropic antenna, you will get a sphere. We are getting a sphere for an isotropic antenna. On the surface, the radiation intensity is same. Therefore, that is will be U average. That is on the surface of the sphere. So I'll start with that. Then consider a directive antenna. If we consider a directive antenna, then the radiation intensity will be maximum along a particular direction. So it will not be on the sphere, but on the particular direction. So U average, that will be the sphere, same as the sphere, that will be U average. But since the directivity, it is a directive antenna, the same radiation power is directed in a particular direction. So in that direction, the intensity will be maximum. In other directions, intensity will be less compared to the maximum direction. That is why in that direction it will be more than the U average. So that is what is shown here by a directive antenna. We show that which is du average, that we have defined. So um is equal to du average will be greater than U average always, and because it is, the antenna is so designed that it is radiating in a particular direction. So is equal to du average. D is greater than 1. By definition, we know D is equal to P by um, omega by 4 pi. So that we are going to use. Now, from this, it shows that there is increase in radiation intensity in the preferred direction over that by an isotropic radiator of same power. When power is same, then by directivity we mean that the antenna has a directivity, means it has increased radiation intensity compared to an isotropic radiator of same power. So that is what is the concept of directivity. Now we'll come to the gain. Gain is another definition. We'll look at that gain. This is 4 pi times the ratio of the maximum radiation intensity to the net power accepted by the antenna from the connected transmitter. So when the antenna is connected to a transmitter, then gain is 4 pi times the ratio of maximum radiation intensity to the net power uh, received by the antenna. So maximum gain will be G, gain is G, G is equal to 4 pi times. Maximum radiation intensity is power given to the antenna is Pm. So G is equal to 4 pi by Pm. That is the definition of As a function of angles, if you want to represent what is the gain, then as a function of angles, G theta phi is equal to F theta phi square. So that is what is the gain. G theta phi is equal to F theta phi square. A power quantity sometimes referred to as a power gain. This is what is gain. This excludes impedance or polarization mismatch losses. We'll consider these impedance and polarization mismatch losses later. We'll take a break here, maybe a 10 minutes break. Then we'll come back and start. So, solar area.